The purpose of this video is to explain the likelihood function that we're going to use when we're doing Bayesian data analysis with binary dependent variables. And binary dependent variables play a really big role in Krushky's text. In fact, chapters 6 to 12 develop many of the ideas of Bayesian data analysis using a simple example of a binary dependent variable, namely that of flipping a coin and getting either a head or a tail. But binary dependent variables are quite common in environmental sciences. So, for example, in ecology, you can think of sites as being occupied or not. In pathology, which is my background, trees are either alive or dead. And in silviculture, if you think about seeds germinating, they either germinate or they don't. So binary dependent variables are really important. So I want to go over a simple example of a binary dependent variable, and I'm going to come back to flipping a coin because that's really easy to understand. I'm going to take my coin, I'm going to flip it 7 times. And my dependent variable, y, is going to be equal to 1 if it's a head, and I'm going to view that as being a success represented by a capital S. Y is equal to 0 occurs when the outcome is a tail. That's a failure, which I will identify as F. And I'm going to have this parameter theta that I'm interested in, and that's the long-term, or long-run probability of success. Or another way to think about it, that would be equal to the expected value of uppercase Y, where this is a random variable, with only 2 possible outcomes, y equals 1 or y is equal to 0. So let's say I do this little experiment of flipping the coin 7 times, and the outcome I get is success, failure, failure, success, success, failure, failure. So that's the outcome of my 7 tosses. And if I assume that theta is equal to 0.6, what is the probability of getting this particular sequence? Well, if theta is equal to 0.6, the probability of getting this particular sequence is going to be 0.6 times 0.4 times 0.4, etc. And that's going to turn out to be 0.00553. And more generally, we could represent this as theta raised to the power of z, 1 minus theta raised to the power of n minus z, where z is the number of heads, or the number of successes, and z is the number of flips. So here's the issue. In reality, we're not going to be concerned about any particular outcome. What we're going to be concerned with is what's the probability of 3 heads in 7 flips. That's what we're going to be concerned with. we're less likely to be concerned with what's the probability of this particular sequence. And so the formula for getting 3 heads and 7 flips is not going to look like a Bernoulli. It's going to look like a binomial. So the answer to that would be 7, choose 3. And in this particular case, if we assume that theta is equal to 0.6, we'd have 0.6 raised to 3, 0.4 raised to 4, or of course, more generally, we could represent this as n, choose z, theta to z, 1 minus theta to n minus z. Now, here's what's really interesting, is that when we're doing Bayesian data analysis, what we're going to do is we're going to ignore this. We're just going to pretend that that isn't there. And that what we're going to do is use this formula. So this is what Krushke uses in chapters 6 through 7 when he's trying to answer the question, what's the probability of getting a certain number of successes in a certain number of trials? So how can we possibly justify tossing away that really important coefficient? And that's what I'm attempting to explain down here by comparing a Bernoulli and a binomial using, as you recall, the basic idea of Bayesian statistics is the probability of theta given data is equal to the probability of theta times the probability of data given theta divided by the probability of the data. And so we're going to go through an example. So let's say we've got a coin and we're not sure what the value of theta is, but we know it's only got 3 possible alternative values, 0.2, 0.5, and 0.6. And P of theta here represents our prior belief about the probability of these actually being the values of theta. So we've got a 20% probability in our minds that theta is 0.2, a 30% probability that it's 0.5, a 50% probability that it's 0.6. These are nice probabilities that add up to 1.0. And here we've got our likelihood function. So there's our likelihood function. And you know the way the likelihood function works is the data are kept constant and the parameter varies. So we're going to keep our data constant at n equals 7, z equals 3. We're going to vary the value of theta from 0.2, 0.5, 0.6, and we're going to calculate these values here using the expression theta to the z, 1 minus theta, the n minus z. So for example, if we've got this sequence S, F, F, S, S, F, F, there's the calculation we would get for theta equals 0.6, and that gives us 0.0053. What we have here is our joint distribution. In other words, the probability of theta and theta. We get that by multiplying the probability of theta times the probability of data given theta, and that gives us this. So you multiply the 0.2 by this, you get this, so on and so forth. And so each one of these is a joint probability with a constant value of data, but different values of theta as shown in this column. And you sum those all up, what do you get? You get the marginal probability of the data P at data. This is what we're really interested in. This is our posterior distribution. This is our posterior. How do we get our posterior? We obtain the posterior distribution by taking, posterior distribution is the probability of theta giving data. We get that, of course, by taking the joint distribution, probability of theta and data, and divided by the marginal probability theta. So here are our different joints. Here's our marginal. We divide each one of these values in succession by this thing at the bottom, and there's what we get. Now we're going to redo this with a binomial distribution. And these first two columns are the same. What's going to change is the likelihood function. So now here we've got the formula for a likelihood function with the binomial distribution. It's got the same thing here, but notice now it's got that coefficient added, this thing of n over z, that I'm trying to show that we can ignore. So these are the likelihood values here. You multiply the prior by the likelihood, that gives you the joint. So these are the different joints. You add up all the different joints, you get the marginal. You divide each one of these joints by the marginal, and here's what we want. Here is our posterior. And we compare that with the posterior that we got using a different equation that didn't have this coefficient, and they're exactly identical. So what's happening? What's happening is that if you consider this likelihood function here, each one of these values is multiplied by 7, choose 3. And when you sum them all up, as a consequence, each one of these individual values, if you consider 7 over choose 3 is equal to 35, each one of these individual values down here is going to be 35 times greater than the values here. The sum is also going to be 35 times greater. So when you divide each one of these values that's 35 times greater by a sum that's 35 times greater, you wind up with the posterior distribution being exactly identical, regardless of whether you use this sort of likelihood function or that sort of likelihood function.